colleagues, my name is Kevin Kotchak. I'm the founder CEO of Chemical Q Device, here for discussion 77. This is April 6th, 2023. So what I first wanted to go over is let's see, this guy is basically this Pennylane. So I'm going to double hash out my comments here in specific. And it's just going through some of these things as, Pennylane, TensorFlow. And you could see basically the big one is Keras. So Keras is the machine learning aspect of all of this. And I'll zoom in a little bit. So basically, you could see number of epochs, layers, train tests. They put these up front. So these are variables that are referred to later on. And you'll see if you don't get this save path right, this image QNN, then things won't work. It'll just give you an error and you won't get the results. And you have to make sure, so for instance, on this one, it's under image QNN, which I created, and you don't want the full path. So if you go to copy path, that one won't work. So you just want the bare folder in there. And what you have to do is you're loading this MNIST data set. So it's a 28 by 28 with this specific one. And you'll have, all these train underscore images in this as well. This 255, you don't need to change. And same thing with the second 255. I learned that in a different tutorial. So you can change this to false, this Boolean, add extra dimension for convolution channels. And then also you could do other things on the quantum aspect of it. So this is the meat and the potatoes of what's being done. So this is basically a random circuit that's being implemented here. So your function is dev and you're calling it a qcnn dot device. And then this is default qubit. And then your wires is equal to 4. And then you have, so default.qubit is one of several Pennylane simulators. I think there's 3 or 4 other ones that work. Some of them won't work, on the quantum aspect of it. And then you have your wires is, equals to qubits. So 4 wires is 4 qubits. Now, these other things, so the high equals 2 is equal to the upper boundary of the output interval. And then also n layers is from above. And then this 4 is referring to some other value. Now, you need to have these 4 classical input values encoded. So this is the beginning. So this is quantum data going into classical data. And then you also need to have this random circuit, so this 4 value here. But if you want to make modifications to the quantum aspect of this program, you do the majority of that here. Now, the 4 classical output values, you'll see this poly Z. So that's common among these quantum convolutional neural nets. And then also, for technical reasons, and if you adjust these values that convolve, you get issues with what the output images look like in your results. So basically, they say it has to be half of the original image. So I don't know if that's a max. And then basically, you'll see it's looping over these other coordinates by 2 by 2 squares. So I believe that's 2, and this is the other by 2. And then assign expectation values to different channels of the output pixel. So this one in specific is kind of laying the framework, for training to occur. So basically quantum pre-processing of the data set. So here you'll see these variables pop up again, this train underscore images. And then again, you'll see other similar functions kind of pop up as well, test underscore images as well from earlier in the program code. So basically you're saving preprocessed images, and this was laid out before. And then this one was run before, so this relates to 50 train, 30 test. Now, for the printout, and you can see that this program has been run before, is basically your plot will consist of 4 of the 10 numbers, which is n samples equals 4. So that's, as you can see, they're kind of showing up there 1, 2, 3, 4. So it picks this 5, 0, 4, and 1. And then the n channels are the top to bottoms. So these are the number of channels that pop up. And usually the last channel has been the one that's been the least detailed. This gray value relates to gray. And then the plot show will show this. This is first channel, second channel, third channel, fourth channel. Or I'm sorry, this is input for MNIST. And then this is first channel, second channel, third channel, fourth channel. It's off by 1 because it starts at 0. And then these are the results basically as the chemical Q device startup got better in this last channel here by some values, both in accuracy and loss. So this is run. And this is the keras, so keras.layers.dense kind of stuff. Now the optimizer can be adjusted. So you can do atom and you could do 9 other ones. So they pick 10. And same thing with loss. So this loss function, you could pick 9 other loss function for trials. So if you really want to get into the quantum stuff, you really have to study existing keras, notebooks, tutorials, these types of things. So here's this being, basically trained, and this is the quantum model, which has the additional, is classical plus the quantum layer to it. And then you can see all the epochs, so 1 through 30. And the ones that show up are the validation loss and validation accuracy. These are the ones that show up in specific on the charts that are going to show. Now, the classical model, and I believe this is how it works, is I think it's just classical. So the quantum one is classical plus quantum, and this classical, because this is how it prints out, it shows that, basically it's similar to a quantum model, but it's, it just doesn't have that quantum layer. And then this is setting things up, and all these things are adjustable in Matplotlib, and in specific, Seaborn is adjusting how things look. And then here's the titles, basically accuracy, and then you have epoch, and validation loss, and then here you go with quantum layer and without. So the blue ones are basically with the quantum layer and accuracy in this one, and then you can see the loss. So I had a loss. I'll show you one in specific that it did significantly better than a lot of the other runs that I did. So I'm going to switch over to Qiskit. And there's a paper that other people kind of in the industry refer to, and it's an author by the name of Havlicek. And if you haven't seen this paper, it's definitely worth seeing. So I'm going to pop over to Quantum Composer, and then let's see here. This is going to go big, and then here. And so in this specific one, basically sharing the screen. Okay, so this should look familiar. So this is IBM Qiskit Composer. And basically what Havlicek did is, this in the specific research group and the associated other authors is they set up basically a framework of supervised learning, and especially with quantum convolutional neural nets, these types of things. So they actually chose to use 5 qubits. So 5 qubits, for classical and quantum. So I'm going to put those in. And then when you do resets, so you'll see the reset pop up there. And as long as it pops up, you hit tab. And then it'll automatically fill in all the resets for you. And then I know I'm going to need a barrier. So you see a barrier pops up. So I can either click that or I can hit tab. And then the other one was basically, measurements. So you see measure shows up. So I'm going to hit tab. And then it's 10 times easier than doing it by hand, even though you feel like you're being productive. So I always like to keep the registers and the reset. And then in this specific one, the author goes Hadamard, and at Q, and this is going to be starting at 0. And let's see. So that's the formula for Hadamard at that specific qubit. And then you could say I got 5 in there. So I want 0, 1, 2, 3, 3, and I want 4. And they actually chose, and I don't think that you need to do this, but it's just interesting. So this is this Havlicek paper from 2018, figure 2, to continue using these Hadamard gates, these single ones. So for instance, they use 3. And it's interesting because depending on the paper, it sounds like you can only use 2 qubit gates. So in that case, if you do, say, for instance, like CXs, so if I do a CX from Q, 0 to, and this is where the creativity lies in these papers, is a lot of times they won't tell you exactly what to do because you can do it random layers, you can do all this kind of stuff. So with these, I'm basically going to set them up. Let's see. This is going to be 2, 2, 3. And then this is going to be 3, 2, 4. This is going to be, see, that should be it. Actually, 1, 2. Yeah, 1, 2, 3, 4. Now, the point I want to drive home here is there's all types of entanglement. So they also call this coupling. So you can have fully entangled, you can have linear. So I believe this would be considered linear. You can have circular. So I just wanted to give you kind of like a flavor that a lot of these circuits can be random. It's just depending on what the function, especially for qcnns, these types of things. So let's go ahead and you see, I needed that barrier there. So, and say for instance, 1, 2, 3, 4, and there's many types of quantum circuits that will run. So the ones that you're trying to find out are the ones that run well, high accuracy, low loss, those types of things. So you can see in specific with this one, and without getting into too much detail, we're gonna just save this. Now, the thing with Qiskit is it'll always say that it's saved, but that doesn't mean the file was saved when you wanted it to. So the foolproof is just to go ahead and click enter, because then you're sure that the title is saved and the file is saved because you clicked enter. So if I do that, and as you see, double checking the circuit, 5 resets, these Hadmards, and then couple barriers, measurements, looks good. And I'm going to go ahead and run this on my, the one I usually choose, which is this Nairobi, which is 7 qubits, 32 quantum volume. And then just real quick, I'm going to pop into jobs to see how the Q is looking. And sometimes it takes a while to establish that. So while that's going, and hopefully I can get to that by the end of the discussion, is I'm going to pop over to lab. So occasionally it'll do this because I think it's to slow people down. I'm not sure, but so the server is running, or it's up and it's going. And again, these resources are free. All this kind of introductory ones are free, so it's worth taking a look at. We'll see if it'll pull up the last files I had up. I think it was just one in specific. So we see this one, and yes. Now, the one with this, so I really like this because it's a high reliance on quantum. It uses a very basic artificial image. So what's imported here that's of importance, IBM Qiskit quantum circuit, it's this Qiskit class. The Z feature map is, I'll show you, it's a feature map that's specific to Qiskit. I don't know if I know Qiskit uses it, and it's full of gates, and it's running on a quantum simulator. And then you have this neural network classifier, which is IBM's thing too, and then this estimator QNN, which Qiskit uses. Your train test split you have as well. So I just want to make sure we're still doing this. Okay. And basically, when this starts off, is The original circuits are the most important things to these. So when it says define this function, now the function is called conv circuit, and it's allowing you, and you can adjust this and you can do whatever. I could add another target RZ right here, you know? So basically, it allows you to do that. And by reading these other papers, there's a preference towards deep networks. So this is considered, I believe, one layer. So you can go deeper as you wish. But you'll see familiar gates, so the RZ gate, the CX gate, and you can modify, this additional RZ as well. So, basically, you can run many, many types of quantum circuits, but finding the optimal one is perhaps a hard task to do. Now, in specific, it says, let's draw the circuit, and it's using matplotlib. And then you have, so the conv circuit builds up into the conv layer. So to show this, because this one is more efficient because it's running, so basically I can autoplay this, and I put a timer in, so it every time it hits this, it gets the time, so this import time function. And I have one at the end too. Now, I'm not going to run all at the same time, but you see here it says start at April 6th. And these things, there's multiple types that you can get through, Qiskit basically. Now, in specific, so, well, let's run these and go ahead and do this circuit. And it's going to print out this, okay? So it's going to use this as the basis of building up, because nobody refers to things as a convolutional circuit. It's going to build up a layer. So that's what this next function is the convolutional layer. And then what this is doing is basically, and I'll show you, it's going evens. So it's going qubits, let's see, or basically it looks at it 1, 2, 3, 4. So it does 1, 2, and then it does 3, 4, and then it does 2, 3. And then when it does 1, 4, that's where you get the stretching of these C0 gates. So you see in specific. So, it was always adjacent, adjacent, adjacent. So it didn't change anything. It's just, it's basically entangling between these different, qubits that you'll see here. So as we could see that the convolutional circuit made up the layer, and all of this is adjustable primarily through the first circuit. And then you can change some things in the layer. Now this is pooling, so this is dimension reduction. And what this does is basically reduces dimensions and reduces computational costs. And it's basically throwing out specific qubits along the way that you don't need anymore. It's basically that you're transferring that information. So for those that are just joining us, basically this is how things are done with qcnns in the quantum world. So in specific, so I ran this pooling circuit. So this is what this is. You can see these are 2 qubits, and then I need to run the pooling layer. So it's using this as a template, and then the stretching or these C0 gates are basically due to its, the qubits, from 0 to 1 or 1 to 0. It's those different qubit assignments. So you can see that now the pooling layer is this big. So for those, and there's many that have taken classical, machine learning, this is how it's done on qubits, and this on a quantum simulator in specific. So if I hit generate data set, now the weakness of this is basically it's artificial data, and they're adding noise to it. So it's more like real images. So additional research is needed to determine whether this can, the requirement is for only artificial data. So I don't believe that's the case, but that's just one of the things, one of these papers I'll be going over. So this generates a data set of 50 images, and I've optimized these values a lot. So this splits up between test size is 30% as written, and then that'd be 70% as train. And then you have basically, these are the outputs. So these are artificial, these are generated data. It has some noise in it. So if I do a quick search for noise, it'll tell me where it just did. My monitor's not the great. Oh, here it is. Okay, so create the noise. So this is inserting noise into artificial data. So again, figure this is like working out the kinks as we wait for the better quantum computers. And then so we have these plots. And then so this is a cool part. So this is a feature map. So the classical feature map that many of you may know is basically that it's not on qubits and it doesn't have quantum gates. So this is what the quantum feature map is. So this specific feature map is 8 qubits, I believe, in stock. Or actually, no, you can adjust it. So it says right here, you can change it to 8. Now this 8 has to match the original convolutional, the first convolutional layer that we had built up from the circuit. Okay, so it basically drew that. And then this is the part that this is assembling the whole, and this is feature map plus convolutional layer 1 plus pooling layer 1, and that goes on for convolutional 2, pool 2. And then you can specify, so you need the 8 qubits, so everything has to match or it won't work, I don't believe. So we had the 8 qubit feature map. And then our quantum circuit, therefore, should start off with 8 qubits. And we're going to call that ansatz, which is like the first initial guess or assumption. And then your first convolutional layer, you'll see, is 8 and, range of 8. And then your pooling layer basically has this format here, these 8 qubits lining up. Now, you can see with the second convolutional layer, it's losing dimensionality. So that's kind of interesting. And then the second, or that's what it's supposed to do. So second pooling layer, you see the 4 qubits. Third is 2 qubits. And then the pooling layer, you can see 2 qubits right here. And then combining all these is basically, should see this printout. I ran it, and it'll basically, I have to draw here, right here. Okay. So this is what it looks like. Now, as it is on the screen, is that basically this vertical line is connected to this. So it goes 8 qubits, so Z feature map, convolutional layer, pooling down to 4, conv pool, and then down to 2. And then here, and especially at the end, you have a single qubit, and that qubit is the one that's classifying. So I think a horizontal line gets a -1 and a vertical line gets a +1. And I believe that's the measurement of the qubit at that single qubit at that particular time is -1 or +1. So on these, basically, more setup. Now, the thing with this also is, beyond that, this isn't actually running real images. It's, artificial images that have noise. This is a launching point, or it's a starting point. So I had to search on GitHub to get this file. No big deal, as long as you know how to use GitHub. And then you're using this as an initial point. So it's not going to take forever to get to whatever you want, right? So this is a big value that was optimized. So, you can change this. This is maximum iterations on the Cobala optimizer. So that goes down to like 100. Or you can change it to anything you want, but basically, anything maybe below 100 might give suboptimal results. Anything above maybe 400, 500, 600 might just take too long. So I'll show you where that kind of plots out. And then especially, so you have here, and this is basically the plot, and this is going to go to 200. See, it's 4, 5, and it's just, it's just slow like that. It's running on their simulator up in the cloud. And then it's plotting on this 12x6, right here that we're seeing. And it's printing accuracy from the training data right below it, but it hasn't done it because it hasn't finished yet. So while that's doing, and that'll just run on its own just fine, is I'm going to go back to jobs. And so the Q, they say it's 1640. So with an estimated wait time of 2 log. So that might not run. It's never that high, but who knows? There might have been some news that just broke, before I checked my quantum computing news, and now everybody's on this specific, you know, this is a real quantum computer right here. So with those demos, and let's see here, and I'll pop back in to see if the IBM Qiskit Q ran. I'm going to do let's see, this one. And the key with all this is research. There's so much that's been done, and I mean, not compared to classical, but as far as quantum progress, that you have to be in tune with, Nature articles and archive articles and just all different types. So should be able to do this. Okay. And then we're gonna present. Should be like this. So this is the presentation, the bulk of it. And, basically it's a bunch of results, this IBM Qiskit, and I showed you these two, is basically in this first one, I was able to get 100% testing, 100% training accuracy. The Xanadu increasing the accuracy, decreasing the loss significantly and getting better images. And basically where's everything going is basically it's a mix of, keeping an eye on the hardware, qubits, bigger qubits, less noise kind of stuff. Now, for those of you that don't know, is basically, this is the framework, is basically inside artificial intelligence, there's machine learning. And inside machine learning, there's deep learning. So deep learning is typically anything that's like 3 or greater layers. It's kind of like fuzzy, but it's around that 3 number. And then a convolutional neural net is basically uses convolution. So to see this conv and pooling and conv and pooling as a neural net. And it's known to work quite well. So you're scanning this image with kernels, and basically you have a collection of these kernels at the end, and then you get a final result, and it's known to go a lot better as opposed to going straight at something. So conv, pool, and in case, you have to have a feature map here, and then at the end, the fully connected layer. So, but that's the general outline for that. And this is basically, I just put all this together so everybody could see, so basically you're having 8 pixels. So 8 pixels is 8 qubits. So you could do the math in your head if you have anything, and I'll show you a calculation that for this specific model that, you can't go too high. I think on IBM Qiskit, you can't go any higher than 62 qubits simulated, but even in literature, I can't find anything higher than 40. So here's some of the hyperparameters, and I kind of touched on before. This 0.3 I've changed all 3 of these, the 50 and the 200. And this is trying to get better accuracy of the testing and training. So in specific, so this is the top one here, and this is the y-axis is not accuracy. It's called objective function value. And then they create an accuracy from that. So you can look up the math, or I could look up the math. And they got 88%. And like I said, changing 3 of these hyperparameters and, with a training value, I got 100%. So I could get 100% on one or the other, but, it's kind of, it made sense to me what I was doing because I had spreadsheets and all these types of things and trying to figure things out. Now the Qiskit, they had 67% accuracy. And then, like I said, so 100% accuracy is basically when it says, like, say for instance, on one of theirs, where it says their bottom right one here, the qcnn predicts this is a horizontal line, and it's basically 2 yellow pixels are saying it's a vertical line. So it knows that, based on original, creating data set, that was incorrect. So they got, 3 out of 4. And basically with this specific one, you see vertical line, horizontal line, vertical line. And I'm not quite sure as far as, when how it picks those specific ones. So this is basically what it prints out. So on the top of this is basically this chart where, it shows that it's going lower, lower, lower. So you could see I had a little bit more iterations, but the parameters that I chose seem to be working more effectively. And again, so this is just for small systems now, but who knows? You know, they say silicon spin qubit, it could be a billion qubits, these types of things, and just imagine. But a 28 by 28 image that I'll be referring to would require 784 qubits. And, you know, we don't quite have that yet as far as, you know, something that's lower in noise. Now, one of the papers did say that since these random quantum circuits are basically immune to noise and don't require QRAM in certain cases, that it might be the case that you can have noisy quantum computers. But the point is this type of model is immune to high requirements for RAM or QRAM. And, you know, it seems to be a high area for research. Now, the Pennylane I was showing you earlier, this N train I've optimized to 80 before, and then inside that quantum circuit that I showed you in the Jupyter lab is basically, I've altered for those parameters. And then you can see, you know, it's just standard 4 qubits, 1,000 shots, 4 layers. And this is how quantum is being used in this convolutional neural net. So I believe it's quite different than the IBM, because the IBM, you know, the pooling circuit and the convolutional circuit were composed of qubits, and you could modify these. And you saw in the code that basically it's just, you know, not as much modification you can do to it. So figure less impact of quantum. And here's some of the results. So basically getting higher accuracy, figure 2, lower loss, figure 4, and then figure 7, better output images. So this is the 4th channel here too. And you can see with the Pennylane, and this is how most of my runs looked. Now I was able to get 80% accuracy in my, like how it looks with that Pennylane. And I didn't get this output quality until I started to see the lower loss. So you see with the quantum layer in specific, the revisions, it dramatically lowers it. And these axes are actually even lower. So this is 0.75 and this is 1. So when I calculate this and put this in a spreadsheet, it's actually, you know, significantly better. So learning from these things. So basically, this is how it goes in structure. So the image is encoded into a quantum circuit. This is for IBM's program, using feature map, kernels for determining features, patterns of particular inputs, and these things are the end results are the same, but the way they work, especially for the pooling layer over the convolutional layer, are different for quantum. So you can see pooling layer, and this is the same thing with classical, dimensionality reduction, computational cost reduction, same thing with classical, reduces number of learning parameters. So basically performing operations, then disregarding certain qubits. So if you have, say, like just 2 qubits left at the end, the top one gets disregarded, and then the bottom one is measured. So, and I believe that's the whole, they call it +1 or -1 for their specific one, which was, you know, basically horizontal line, I think was -1, and then a vertical line was a +1. So that it's all whittled down to a single qubit. So you could start off, and that's for binary classification. So that would be different, you know, if you would want to do multi-class. So for training, basically these parameters are tuned to reduce the loss function. Any parameterized circuit should work, but results will vary. Fully connected layer determines classification. So that's at the end. And this is thought to be a strong point basically for this is, you know, ion trap hardware. This, you know, can do fully connect, meaning that all-to-all connectivity kind of notion. Now, and this is Kong et al. And these next couple papers are kind of famous for quantum and convolutional neural nets, and they're found in other people's works. I think I got one from IBM Qiskit. I got one from Pennylane. You know, so they're quite common. So they range from, I think, 2018 to 2019. So basically, this log base n variational parameters. You know, this is the quantum advantage, the mathematical advantage is, you know, you don't it's not exponential, in multiple things, kernel size or runtime or, parameters, these types of things, and connects volumes of multiple feature maps to other volumes, extremely large, and these many-body Hilbert spaces. This is a key principle. Hinders. So it should read is basically if it was with classical. And then number 4, it's based on this MERA circuit. So a MERA, this is a Nature article by Harvard and Berkeley, so Harvard University, and then UC Berkeley. And a MERA basically gets exponentially bigger, and then a QCNN gets smaller, and it can't get exponentially smaller. But you'll see the differences. Now, they also say that the QCNN, and I don't know if this is just 100% the case, but it also contains this nested quantum error correction circuit in there as well. So this one is the Henderson paper from 2019. So quanvolutional. So quantum convolutional and quanvolutional are the same thing. So it's just quanvolutional is a shorter form of saying that term. So powering image recognition with quantum circuits. So you'll see the future, more images, bigger images. So this is likely talking about hardware, like real quantum computers, a bit more qubits, bigger kernel sizes. And then in specific, these smaller QNN circuits run on single data points. So in that specific case, that it's not taking up a lot of what would be QRAM, So that's a key thing. And then ML algorithms are probabilistic, but suffer with compute, the actual, the energy of computing, these, and then quantum circuits, and you've heard these things like bidirectional, probabilistic, and has exponential potential. So everybody basically wants these, awesome quantum computers to pop up. And then basically, so you have these extract features from input data by transforming a spatially local subsections of data. And then to continue, the number of qubits in the convolutional filter does not need to match the dimensionality of the input data in general. So you can have bigger circuits, like your circuit designs, and you can adjust with it a little bit. It's a little bit flexible. Now, they did say a lookup table in their specific one was applied on each new input set of data, as opposed to running everything through the quantum circuit again and again. And then future questions to consider: do certain structure convolutional filters work better? And what minimal convolutional filter gate depths work better? How data dependent is ideal set of convolutional filters? And then how does encoding and decoding approaches influence results? So this is basically like the beginning of a quantum circuit, and then you do some other things, and then you're decoding or measuring, basically. So this Havlicek paper is basically based on the specific circuit that I ran, a modified version of that. And as you see, support vector machines. They're expensive to run with large feature sets. Variational circuit classifier similar to SVM. And in both of these two approaches below, the kernel cannot be estimated classically. Has to be quantum. And then approach number 1, quantum variational classifier, increasing circuit depth improved. And this is this image basically, as you go deeper in the circuit, meaning not more qubits, but more gates on the same layers of qubits, help the results. And then approach number 2, quantum kernel estimator, estimates the kernel function and a classical SVM for classification. They actually kind of experimented on their own hardware, and this is in 2018. And then, so basically, moving forward with all of this is the goal is to get these bigger neural images. So the stock, these come 512 by 512. And then, as I show here, I can reduce to 256 to 128 to 64. But, based on these other things that I've shown you, is that, in certain types, so if you went full out and had your convolutional layer and pooling layer composed of, qubits with gates, that's a high demand, basically your pixel size can't be too high. But if you're just going to use it for, this kernel type function, and it's just a very specific, 4-qubit thing, you can do that. And other people have done that with good results, but you also need to have, say, for training, some other neural net, like, oh, not ImageNet they were using, but these standard other ResNets, those types of things that you need to use in addition to the quantum layer. And it's basically getting these 5,000 plus images into something that's practical with quantum. So the hope with all of this is basically NSS practical quantum computer forecast this year. The government is 110% behind quantum. INQ, manufacturing facility next, first half in 24. So there's lots of promise for this. So there's also these single qubit encoding. So imagine getting, classifying off a single qubit. And I think that's the whole way through, because we did that here, but that was at the end. These scalable quantum convolutional neural nets, and it's called PVM as well. So this is basically what set up to get the better results, compared to the manufacturer or of the program. And then as you see, these don't show the 100, but basically things that tended to work well as opposed to other based on these kind of 3 key variables. Now in this specific one, and Pennylane is basically, you have your 80 train, that seemed to work the best. I tested it, so like anywhere from like 76 to 84 seemed to work well. And I could kind of see towards the end of that 84 where the accuracy, wasn't quite as good. But there's always also loss with that too, and that's what I calculated here. And this is what this shows is the IBM, the training testing 100. And then also with that Pennylane, the 72.9% average accuracy. So I took all 30 epochs and just averaged the accuracy. Did the same thing with the original program, so close to 49%. And then this was, that the loss was a lot lower, so 0.872 compared to 1.38. So that was a win right there. And I can't stress this enough. It's basically your input data matters a lot. Like I said, this Kaggle 4-class or multi-class brain tumor data set, probably not ready for that IBM or the Pennylane, but learning from all of these things and putting these things together, what would be, something to try basically to get these results. And then, here's, so Qiskit, most upgradable for quantum. So these two vary. Like I said, the Pennylane is just a very simple, and I think it's just a kernel that's based on quantum as opposed to Qiskit with the convolutional pooling, layers, based on qubits. And then this conventional one, obviously getting able to import the bigger data sets and reduce them, and still classically either on this or other modern hardware, is that you're not able to do likely 512 by 512 or 256 by 256 stock training testing with any type of efficacy. And basically in these things, also incorporating IQP, it's a more challenging encoding set, preparing code based on an industry forecast and progress as well. So these were run, so in specific, so the circuits on the top two were run on quantum simulators. I ran them on the real hardware, and I believe these fall under the case of random quantum circuits. So there's one of these papers, I think that maybe the Henderson one, is it couldn't stress that enough. Now, although they're random, they're used for, basically doing not the training and the testing. They do serve a function, and they have increased results, say 4 or 5%. But you can see the CNOT laser are different. So this one would, I believe, be called linear entanglement, the blue ones. And they're circular, there's fully, I don't believe either of these are considered fully entangled or fully coupled is what they'll say. And then the bottom two, I couldn't quite get a good enough read on exactly what the circuits were, but they're similar in function to the first two. and expect probably similar results on the probabilities in the blue. And basically, this is the brain tumor, 5% increase, and then these last three, showing just with a simple, and I know I'm pretty sure about this one is there's no additional QRAM requirement on these quantum circuits, so that's good. And then these are looking forward is this classification. I might need to boost that up because there's certain parts that are just, it's just well known. And then, getting to that next step, if it's a prediction, or it could be, just a more complex classification problem, that might work too as an MVP, and kind of like the hardware, how things are looking there. So that's that. And then I'm going to check on this IBM that's been running, so in the jobs. And it's just, it's just like that. Maybe it's down or something like that, but that doesn't look like that's going to happen. So here we go. And, right. Yeah, the other, actually, I do want to check. Let's see. Okay, so this is in lab. And then this should be done as long as that didn't, let's see here. And screen. So on this specific one, so remember, imported the time. Now I didn't actually do this, everything just, the trick with that is you just run all cells, and that's accurate. So remember, I was just going through step by step. So this created the first stamp right there. And then going down, and the important thing to do is, so maybe when I exited, okay, yeah, maybe when I exited. So I've shown you kind of like the results with that one, and then we'll switch over to discussion kind of here. So here. Okay, so should be able to come on. Unmute. Yeah, it should be able to come on. And then, it's just kind of interesting because a lot of people define quantum advantage as having like universal quantum advantage, where you have specific maybe sets of computers, and they're, across the board, it's just exponential, exponential, exponential. But from what it looks like in literature is that you can do, especially, without, assigning qubits to the pooling layer and the convolutional layer, is that you can do little tricks with quantum that don't require QRAM, and that's basically looking at like a single pixel at a time. So it's not like a full image, like basically where classical would bog down a little bit. So any questions or comments? And then feel free to unmute, or you could come on, and then also you can put stuff in the chat as well. But go ahead, Ron.
Hey, Kevin. I think it was in your first code demo, you had mentioned you had 8 qubits and associated that with 8 pixels. Did you get some sort of sense of how those pixels would be arranged, or?
Yeah, I mean, there's diagrams for it, and basically, I've seen it. Where's this at? I saw it on it was like a video presentation. Another one, if you had like 4 pixels, that's like a 2 by 2. So each of that, like that single, top left pixel goes to a specific, that qubit in that encoding circuit, and then like the other 3. But as far as like, how they're picked, to go kind of sequentially or those types of things, it wasn't quite apparent.
Oh, okay. So it's, if you had 8 pixels, that's typically represents a image, like a 16 by 16 image that's 1 bit deep. So it's like a black and white image. It's 16 by 16.
Uh-huh.
Does any of that sound familiar?
I mean, no, I mean,
And
everything's,
what they do is that image is amplitude encoded.
uh-huh.
So they manipulate the state of those 8 qubits such that when you arrange the state vector in a 16 by 16 grid, those amplitudes are supposed to somewhat draw the picture or represent the picture. And again, it's black and white, so it's only going to be it's a single bit. Although I guess if you're amplitude encoding, you probably could encode more than 1 bit, but I guess it'll depend more on the hardware.
Yeah, I mean, in the case of the IBM is basically everything that I saw. So if you want 28 by 28, it's literally 28 by 28, and it's that 760 qubits requirement kind of thing. Now the Pennylane one, it's just using a 4-qubit quantum simulator, this random circuit, but you could change it to get better performance, kind of thing. It's a 28 by 28 MNIST, and then it's reduced to 14 by 14. So I think at the minimum, it's able to do the 14 by 14, and then at the max, and like I said, I don't think it's doing the 28 by 28. However, when it cuts it in half, I think that's where a lot of the accuracy is lost, or maybe even the loss is increased too. Is basically in order for that 28 by 28 to fit in, they basically reduced it to half. So
Well, I think that the 28 by 28 goes through some convolution filters or convolutions for dimension downsizing. I'm thinking because most of the examples I've seen for quantum image processing require only work well if the dimensions of your image are a power of 2. So 16 is 2 to the 4th. So the next size would be 32 by 32, which would be 10 qubits could do, I think, 32 by 32. You get 5 per edge. You can change that too. I think you can if you do 6 and 4, you could make an image that's 16 by 64 maybe. But yeah, I was just curious because when you said that, I wasn't really understanding how those could be individual pixels. But now that I'm thinking back, some of the diagrams you showed, the very last channel that you show, if you look at it closely, those are actually 16 by 16 images.
based on the scale.
Well, no, based on the plot, you can almost figure out, look and see, or just count the pixels because they're so big. But
Yeah.
if you look at the dimensions, so if you look at the very top row, they're 28 by 28. But when you get down to that bottom row, it seemed to me, anyways, that they were 16 by 16. So
Yeah, I know all 4
probably makes more
channels.
sense.
Yeah, all 4 outputs are identical, so in size as they should be, because that there was an initial change to have them.
Well, yeah, but I mean, even in classical machine learning, that MNIST or minced thing is traditionally done. The very first layer is a convolution that is a size reduction.
Oh, okay, so
Yeah.
that's standard for.
That's pretty standard for classical machine learning. And and for that particular problem, again, it's what you're trying to do is identify handwritten digits. It's really a good solution because you really don't need 28 by 28. You don't lose, although you lose. Like you were saying, if you just take it down to 14 by 14, you're losing 75% of the pixels. You're not necessarily losing 75% of the information, though. So that, and that's all the part of the machine learning engineering, is you have to know which type of layers suit your problem. I'm sure it'll be the same thing with the quantum stuff. You'll have to know which type of quantum neural net, quantum convolutions or quanvolutions, like you said, best serve the problem at hand.
Yeah.
But I think it's actually pretty cool that you've gotten as far as getting the quantum version of the thing to produce the results you're getting. So it's pretty impressive.
Yeah, I appreciate that. It's kind of interesting because, like, wouldn't it still matter, like, that on accuracy or loss? Like, I understand, like, you can still, if you have it, tell a 1 from a 0. But wouldn't that affect? So you're saying that standard, it doesn't affect anything, or?
I'm not really tracking your question.
So you said the first operation done is typically convolutional, where it's just cuts
dimension reduction.
Dimension reduction, which is kind of like pooling. It just cuts it in half from the beginning. But
pooling's a little, well, pooling's is also a dimension reduction step, but it's a little different.
Yeah. What's interesting? Go ahead.
In traditional image, I mean, a lot of this comes from traditional image processing. When you have a big image and you want to scale it down to a thumbnail, there's tons of algorithms out there that you can choose to do. The simplest algorithm is to just throw those pixels away. The ones, if you're doing a 1/2 on each dimension, for every 4 pixels, you're just randomly or not randomly, you're actually throwing 3 specific pixels in every kernel away. You just throw it away. That's the simplest thing. The next type of convolution is where you calculate the average of those 4 pixels and replace it with 1 pixel. And there's variations on that, and that's where you're talking about using a convolutional kernel. There's lots of different convolutional kernels that will do size reduction, and you pick the one that works the best for your class of images. So a photograph of the natural world might use one kernel. They may find that the kernel you want to use for these synthetic medical images might be slightly different, because it's they have weird contrast. If you look at some of that stuff, they have things that are at both extremes of the contrast range. So there might be a convolution that reduces those better.
Yeah.
But actually, some of the stuff I've seen for quantum is one of the things that quantum does really well is that step of dimension reduction, but it does it in such a way that it figures out which pixels in each group are meaningful. It sort of has this, the business of the of patterns that support each other and patterns that interfere with each other. So it's using that quantum technique to figure to basically what it'll do. It'll amplify the really good pixels and the really bad ones, and then the really bad ones are easy to pick out with classical circuits, because they stand out like a sore thumb. You can just remove them. So hopefully you get a better quality image reduction by using quantum for that type of layer. I'm not really sure from that tutorial what else they're doing with quantum. I'm sure there's other algorithms that would help you along in the classification step.
Which one, the papers or the IBM or the Pennylane?
The one I'm looking at was the one that had you're doing the one with the minced characters. Yeah.
Okay.
Yeah. It looked like they were using quantum. I've seen some people refer to it quantum image compression, or it's basically quantum convolution that does a better job at reducing the dimension of the image without preserving even more information. So again, you're throwing away data, but you're not throwing away information. That's the big goal in all of this, even in the classical side. And so the idea is if you do it with a quantum machine, you can improve that ratio so that you're still throwing away the same amount of data, but you're keeping a higher percentage of information.
Okay. The amplitude?
Mm-hmm. Yeah, and again, it uses the interference or these interference patterns that that are subtractive or additive, and and this is real classic with the quantum, like the Bell states and stuff, where everything sort of kind of gets forced into two different categories, and then you're scaling that up to more than 4 categories. But again, one of the categories is this is a really good choice, and the other category is this is a really bad choice. But it has a way of marking the bad choices such that the classical, you can turn that over to the classical and they can remove those easily.
Yeah.
And so you get an image that is downscaled nicely, but didn't retained a higher percentage of the information than with just normal classical convolutions.
Yeah. Yeah, I guess the first thing was kind of interesting is they said instead of pooling, you could do mid-circuit measurement like dynamic circuits. So just measure like right in the middle of the circuit. And then for the, say like standard convolutional neural nets, I see some exotic ones along the way. So that's my question is basically, as far as the innovation behind all of that, is that just like we got a better, classical computer and now we can run this, or is there something more to that, or?
Well, we're going to be in the hybrid business for for the foreseeable future. And again, you're using the quantum stuff, the quantum hardware to do what quantum does well, and then it's just like Shor's algorithm. You use the quantum stuff to do the period finding, but you take the results of that period finding and turn it over to a classical machine to finish the job.
Yeah.
So it's going to be the same thing with this, but
yeah. So I'm guessing there's going to be an art to that as far as
absolutely
hybrid, for sure.
Well, quantum machine learning is in its infancy. It's like what machine learning was 10 years ago. And hopefully it catches up faster than machine learning did. I mean, the people, it's the state of the art in classical machine learning is pretty much everybody is like all excited about transformers. They're just like, we're not so crazy about neural nets that much anymore, or convolutional stuff. We're into transformers because everybody is so excited about Chat GPT and things that fake artificial intelligence and stuff, and Google is out of their mind because because like the Chat GPT from Open AI is kicking their butt. I mean, Google has all that power behind their search engines, and Chat GPT is actually more conversant and can answer your question. Whereas when you ask Google for something, it's, here's some websites. So this is what's behind. I don't know if you remember hearing a month or so ago, Google laid off a whole bunch of developers because they realized they need to pivot hard into this AI. So there'll be something coming from Google to compete with OpenAI's and Microsoft's GPT-5, for example. Yeah, which will be good because then there'll be more players out there, and hopefully the cost of using some of those high-end services will go down.
Yeah, very cool. I just love this technical stuff, reading the papers, and then what you said kind of triggers something because I was thinking like, there's like a trend, that somebody gets from a paper that just come up, they'll publish something, but there's other information that was lost you know, say from years back, and you hear that story of like somebody having a breakthrough, like digging through old research papers, that kind of
Yeah.
stuff. But it'll be kind of that, and it's interesting because you said the whole hybrid thing, you know, it's going to be an art form, you know, meshing these two together for
Yeah.
QCNNs, other aspects of QML as well.
Yeah. And it's going to be here for a while, obviously. So,
Yeah,
but
awesome.
I had seen some, speaking of, you know, in other areas, I'd seen some articles via, I guess it's physics.org or ScienceX, I can't remember. There's some people doing some cool things in sensor technology.
Yeah,
Some new things, I haven't had time to go read everything, but
I found a bunch of
it's pretty
stuff,
cool.
you know,
Yeah.
say August, September last year, and it was just, you know, this rat's heart with it was a diamond quantum sensor, and then I think it was an order of magnitude better sensitivity, and then there was the a double diamond sensor for batteries, and that could have applications for medical too. And you know, they've tried it for in vitro brain, and you know, it's that's kind of for sure. Yeah, Fermilab is basing everything off of, you know, a new MRI analysis is based off of quantum sensing and quantum computing, and then Bosch is into this diamond quantum sensor. Yeah, and this is, you know, is what's the scope, you know, for me, because I can't, you know, focus on sensors getting that data. So this is the data acquisition phase in medical image processing. And then I'm way down where I have the data, you know, so pre-existing images. So this MNIST data set, there's medical MNIST, there's the Google Kaggle, brain tumor, you know, I've seen classifications go up to maybe 8 or 9 types of classifications, but you know, it's just you have to find out what's actually going to be useful in the future. Like, is that useful to have 10 brain tumor classifications? I know that the variance appears to be much greater than that of some other dementias. You know, it's just a gradual kind of you know, the hippocampus shrinks, more cerebral spinal fluid, those types of things. So yeah, it's all like somebody said before, it's a killer app you look for basically, and you know, something that works really, really well, and it's hard for other people to do. It's there was a let's see, Peter Chapman. There was an investor call this week, I believe, or no, it wasn't an investor. It was a reputable site though, and he said expect the Chat GPT of quantum computing in 2.5 years. And he also said there's a demand, you know, for people that understand quantum and program quantum, those types of things, because it is a steep learning curve, you know, from people that were taught conventional physics and, you know, classical mechanics, these types of things. So it's taken me 6 or 7 weeks to kind of, you know, wrap my hands around it a little bit.
Yeah. Well, for example, this one, the first one I'm looking at here is a new quantum sensing method holds promise for improving greenhouse gas detection. And I went through
Yeah.
the synopsis, and basically, it's a new scent. They're not giving too much
Yeah,
information on the
there's
hardware, but
basically
they're able to more accurately measure the frequency of light with these quantum sensors, and so like gas chromatography is,
yeah,
you know, they're saying will get a lot better, and
the,
that gives them the ability to spot really tiny amounts of a certain molecule, so
yeah.
that, you know, that's gonna wind up in medical land for
Yeah,
sure.
there's at least 3 that have gotten big. The first one is the whole superconducting. What do they call that?
Yeah,
It's literally like you go to the hospital, but the issue is the standoff distance because it takes liquid
yeah,
helium or nitrogen, or you know, mixture of those two, something like that. And then there's the one that kind of had a lot of promise was OPM, optically pumped magnetometry. Now, between those two, they could only do magnetic information, I believe. Now, with the diamond quantum sensors, they can do electric, they can do magnetic, they can do temperature. I think they can do force and one other one like strain or shear. So, and the diamond quantum sensor, because of its simplicity relative to the other two, can place a lot closer. So I actually think the one that I was looking at last August or September in Nature, it wasn't the best performer compared to the OPM, but it would since it could be placed a lot closer and it's inert and they want to do these quantum sensing inside cells, and human bodies, all that kind of stuff that
Yeah.
it kind of has the greatest uptake to it. And not only can you do NV center, you can do silicon vacancy. I think you can do phosphorus too. So it's it's cool stuff, but all that falls into basically getting better data. So that first step of medical image processing is data acquisition. And then the next step is like a reconstruction algorithm, and that's basically I'd be looking at that next year, Q2, and there's already an MIT paper on it by Seth Lloyd.
Yeah.
So
Well, there will also be, like, just now the big thing in high performance computing is you'll hear the phrase in-memory computation. Have you heard this one?
no,
So basically, instead of, a traditional PC like you might have on your desk has a CPU, has a chunk of memory. It has other storage mediums, but the processor has to go out to memory or a storage medium, suck in a program, execute it, and store the results back out in memory. What they're talking about is the memory locations themselves will eventually, every memory cell will have its own ability to compute, or every small tiny cluster. And this is kind of one of the things that, like, NVIDIA is doing with their, if you look at their architecture,
yeah,
they've got area managers and tensor managers and stuff going on there. So they're kind of doing that. So it's called in-memory computation. So it saves the time of having to ship the memory, ship the information from memory over to the CPU, do something to it, and then ship it back to a memory location. They're just doing everything in memory. Well, the same thing is going to happen with quantum, and quantum diamond vacancy sensors are going to be ripe for that. Once they figure out a way to engineer the carbon lattice to a specific array of vacancies, and the ability to have the channels between the vacancies, now you're going to have a sensor where you can do a whole bunch of the quantum computing right at the moment in time it acquires the thing,
yeah,
acquires the data. So it's fascinating what could happen.
yeah. Awesome. This has been a good discussion. This has been discussion number 77. This is April 6th, 2023. Thanks everybody for joining, and have a good night and have a good productive rest of the week. Take care.
See you, Kevin.